So this is really great pleasure for me to introduce József Balogh from University of Illinois, because he is a really great mathematician who has many great works in extremal combinatorics, random graphs, and other fields of combinatorics. And today he will speak about independent sets in regular graphs.
So thanks for the possibility to give a talk. It would have been nicer to give it in a person. So I talk about independent sets, and I try to make a new talk to talk about some recent development. Some of the results was proved yesterday afternoon, so it's really fresh. And that's my first online talk, so if there is any accident, then please forgive me. So the study of independent sets in regular graphs goes back to at least to the 90s. The many paper sites Granville who posed this question, that what is the maximum number of independent sets in a deregular graph? And in a very nice paper, Jeff Kahn proved using entropy method that this maximum is achieved at least when we restrict ourselves to bipartite graphs by vertex disjoint copies of complete bipartite graphs, KDDs. And it remained as a challenging question to find this maximum for every graph. And Yufei Zhao, while still as an undergrad, found a very nice switching trick where he transferred Kahn's results from bipartite graphs to every graph. So he proved that this maximum, the number of independent sets are maximized by vertex disjoint copies of KDDs. And in the beginning of this year, Cohen, Perkis, Sarantis, and Tetali posted a paper where they looked K-uniform hypergraphs and had some results and questions about what can we say in the this setup. And I mean, this conjecture is not in this way in their paper, but they speculated that this maximum should be achieved by vertex disjoint copies of some small hypergraphs. And a natural candidate for this, based on the graph case, here I restrict myself for 3 uniform hypergraphs. So a natural candidate is that we take a complete 3-partite hypergraph and then take vertex disjoint copies. And here for this problem, we had an unpublished observation joined with Bela Bollobas and Bhargav Narayanan that we posted in this year on arXiv, that one can do better. So let me try to describe in this picture that what could be a better setup. This setup works for K-uniform hypergraphs as well, but easier to describe it for the 3-uniform setup. So I partition the vertices into 3 parts, and between 2 parts I restrict myself to a matching, and between the other part I consider as star, and I do it for every pair. So between this, in this picture, I consider a matching of size 4, like it's a pair of vertices, and each matching edge is extended in this picture 4 different ways to get 4 hyper edges. So in this setup, we will have sorry, I still have to get used to this pencil. So in this setup, we get 16 hyper edges. And we conjecture that this hypergraph is the one which, given regularity condition, maximizes the number of independent sets. And the reason for this that it beats the complete, let's say, 3-partite hypergraph is that the number of independent sets seems to be the same, but here the degree of vertex is 4, while if it was a complete 3-partite hypergraph, then the degrees would be 16. So we can get the same same complexity for a lower degree, and we prove some a partial result for some family of hypergraphs that this is optimal. So with this example, I just wanted to show that independent sets not always behaving like as we think. And from now on, I will restrict myself to graphs, and in particular, I will restrict myself for hypercube or to the Boolean lattice. So let's look as a warm-up the number of independent sets in the hypercube. So a trivial lower bound is the following. So we know that the hypercube can be split into, or can be looked as a bipartite graph. One class could be considered as the set of even vectors where the sum of the coordinates is even, and the other class has the so-called odd layers, and we can generate many independent sets that we decide if we want to work with the even layer or the odd layer. So we get a factor of 2, and we can take an arbitrary subset, and we generated an independent set, and then this annoying -1 is there because the empty set is counted twice. And one can improve this little bit, that let's say that I choose one vertex from the even layer. I call this, or it is called like as a defect vertex, and then choose the rest of the independent set from the other layer. So I get the factor of 2, deciding that which layer is even, which is odd. I have this 2 to the n-1 choices for the defect vertex. I lose this 2 to the n factor because if I put this defect vertex into the independent set, then its neighborhood is not in the independent set. And for the rest of the odd vertices, I have a choice to put it in or not. So I generated a significant amount of independent sets. And I can boost this argument instead of choosing one defect vertex, I can choose I defect vertices. Then for the number of choices, I get this binomial. And assuming that I manage to choose the vertices far from each other, I get distinct neighborhood, so I lose I to the n. And it's very few cases when it doesn't happen, so it can go as an error term. And I generated still many independent sets. And summing it up, we get a nice sequence, and we get E as a constant factor. So we generated 2 times square root of E times the trivial lower bound many independent sets. And it was proved by Korshunov and Sapozhenko a long time ago that this trivial lower bound is actually asymptotically sharp. And later Sapozhenko gave a different proof where he used the graph container method, and I put here the word that's sophisticated, and maybe later from the talk it will be clear that why I say that sophisticated. And in US, this result was extended, popularized by Galvin, who was motivated, studied by Hartford model, and counted weighted independent sets. I will not go into the topic of weighted independent sets. And there was recently a paper of Jensen and Perkins where they computed the many error terms, and they used the cluster expansion and abstract polymer models. And this hypercube was very popular, like Galvin counted the number of proper coloring of the vertices. Here he again had this nice constant E. Then Kahn and Park recently counted proper 4 colorings of the cube. This E is still there, but the exponent is different. Jensen and Kivash announced that they can count proper Q colorings, though the manuscript is not yet available, or at least I haven't seen it yet. And other topic is that, or other result by Kahn and Park, who counted the number of maximal independent sets. Here the maximal means that non-extendable, but doesn't mean that the size is maximum. And note that the constant E disappeared. We have a linear factor n, and the exponent dropped a little bit. And relative or a similar model is the Boolean lattice. So the difference between the Boolean lattice and the hypercube is that the hypercube, between two sets, we put an edge if one of the set is contained in the other, but their distance is 1, while in the Boolean lattice we have just the general containment. So let's say that in the Boolean lattice, every anti-chain is an independent set, but is it correct? But not every independent set is an anti-chain, because if two vertices are at least distance 2 from each other, then there is no edge between them in the hypercube, but containment relation is a possibility. And but if we restrict ourselves to the middle two layers, then the anti-chains are the same as independent sets, because there is no space to separate from each other. And a classical theorem is by Sperner, who proved that the largest anti-chain in a Boolean lattice is one of the middle layers. And there were many results about it. I skip many of them. I just mentioned that Orsthus in 2000 considered a random variant of the problem. So for some p independently, he kept vertices of the lattice with probability p, and wanted to determine the size of the largest anti-chain in this random setup. And the expected number of the largest anti-chain is, at least the from Sperner theorem, is p times n choose n half. And what he proved, that if p is much larger than log n over n, then one cannot do anything better. And here for this problem with Mycroft and Treglown and independently Colares and Morris, we proved for all the range of P the same result. And here the new technical phenomenon was the so-called two-phase graph container. So the two-phase graph container is simpler than the sophisticated graph container, but one step ahead of the simple graph container that I will briefly talk soon. And here I should note that Ham and Khan in 2019 proved that the largest anti-chain in this p-random subset is actually one of the middle layers. So it's not the sizes as much, but the layers when p is almost 1. Note here that 3/4, it's not if p is less than 3/4. Interesting that put up in their paper about the Erdos theorem in hypergraphs, and they just get it out from their method. And I will talk about this relationship now. So probably most of you know Erdos theorem. So it just says that if we have a k-uniform hypergraph on n vertices, then the largest intersecting family, the one which is trivial or star, so which contains one vertex. And with Bowman and Mubai, we started to look the Erdos problem in random hypergraphs. So we keep the vertices of k-uniform hypergraphs with probability p, and we were interested to find the maximum size of an intersecting system. And for a while, nothing happened, but after like 6 years, there were a series of papers on the topic, including some local people from Moscow, and try to connect the two problems. the counting independent set and the Erdos corridor. So if somebody tried to solve some problem on intersecting hypergraphs, then probably then he or she knows that one of the hardest cases is when n is equal to 2k plus 1, where k is the uniformity and n is the size of the underlying set. So assume that we have an intersecting family. Then we split the hyperedges into two classes, A and B. I put hyperedges into class A, which contains the largest element 2k plus 1, and I take out this element 2k plus 1. And I put the other hyperedges into family B, which don't contain element 2k plus 1. And I take the complement of this family, so I create family C that I take the complements of sets from family B, but I ignore now the element 2k plus 1. And I compare now families A and C. A is a k minus 1 uniform family on ground set size of 2k. C is a k uniform family of size 2k, and A and union C is an independent set. When I put an edge, if one set contains an others, I could say that A union C is an anti-chain. And this follows from that F was an intersecting family. So if we have a set C and A such that A is subset of C, then looking back that how did we get I can't figure out how this works. So I try to look how we get set C. It was obtained from complementing an element of B. So this 2k minus C is in B, and this disjoint from A union 2k plus 1. So we get two sets in F, which are disjoint, and it contradicts that F was an intersecting family. So this is a relation between intersecting families, or maybe intersecting families and independent sets. And most of the rest of the talk will be about the middle two layers of the hypercube. Like in the previous page from Erdos Rado, I get into just the two layers. So I restrict myself to a ground set of size 2k minus 1, and I look at k element sets and k minus 1 element sets, and we put an edge if one set contains the other. And let's try to count the number of independent sets. So I follow the pattern that we had from the hypercube. I want to give a trivial lower bound, which is coming that I take either a subset of the top layer or a subset of the bottom layer. And I try to give a reasonably easy upper bound. And the reasonably easy upper bound is coming just from the simple graph container method. And that's so simple that I can try to, do you see this enlarged thing on your screen? Or
Yes.
I did not intend to do. Is it normal
No, it's
back
fine.
now? Okay.
Yeah.
Sorry. So I try to give a sketch how this simple graph container works. So usually for this container method, we need some super saturation, and Clayton proved the following in the 60s, that if we take a subset of the hypercube, which is just t larger than the largest layer, then the number of edges will be at least t times k. And if we use this super saturation, then we can conclude that for every independent set, we can find a certificate set, and the rest of the set with the following properties. So further, the certificate is small, like the size of A is small. And second, that the rest of the set is not very large. And the independent set is a subset of A union X. And the proof of this is really just the greedy method, that I put to the set A always largest degree vertex of the remaining graph. Then I know that the neighborhood of A is not part of the independent set, because by definition, and it means that if I put into the set A a vertex of at least root k, then I remove at least root k vertices from vertices which could be potentially in I, and greedily I can do it as long as I don't reduce myself to close to the size of the middle layer, and I know that my independent set I will be subset of this. So it's really simple. I'm not sure that I give the best presentation of this, but here nothing fancy is going on, and it's a question that which bound could be better, the trivial lower bound or this simple upper bound. And that was the problem that we tried to look. So if we go back to the hypercube, then just recall that we looked at trivial lower bound, and then we started to get more independent sets by slightly modifying the trivial way of generating independent sets. So let's try to do the same thing here. So I have the top and the bottom layer. We can generate easily this 2 times 2 to the capital N many independent sets. And now I try to add this defect vertices. So I add, let's say, one vertex to the top layer. Then I have this capital N many ways to choose it. It has k neighbors in the bottom layer, so I lose 2 to the k ways of extending this, but note that 2 to the k is much less than capital N, because capital N is about 2 to the 2k. So I generate actually many independent sets, and I can keep going only if I add I vertices to the top layer, I can do it and choose I ways, and assuming that these I vertices are at distance at least 2 from each other, I lose only 2 to the I times k possibilities to extend it, and some computation gives that this is maximized when I is about 2 to the k approximately. And if we try to count it, then with a little bit more care, then we will see that if we choose this 2 to the k many random vertices from one layer, then about k to the 3 pairs of vertices which are at distance 2 from each other. Why is it relevant? Because for a pair of vertices, instead of getting this minus 2k in the exponent, they have a common neighbor, so a +1 will show up in the exponent. But this seems to be like a lower order term. And the main result of this talk is that with Garcia and Li, we proved that this way of counting independent sets is actually asymptotically sharp. So if we look the formula, then we get the two that the symmetry of the top and bottom layer. Then this 2 to the n is coming from the term that we can, for most vertices, we have a choice to from a layer to put it in or not, and this n to the 2 minus k is coming from this defect, and this second error term is coming from the pairs of vertices which are at distance 2 from each other. So here I just explain this maybe better. So again, this is about just 2 to the k, and that error term is about k to the 3/2. Okay, and a little bit embarrassing to admit that when we get this formula, when we try to do this easy way of counting from below, we couldn't actually match it precisely. So somehow it was not easy to count. I will talk about this later. So in the next 10 minutes, I try to talk about a little bit of the proof of this, and after I will switch back to talk about several things. So in case if you get lost in the proofs after, there is a hope to get back. So here actually I try to define things which were coming from Sapozhenko's graph container method. So I assume that I have a bipartite graph with parts x and y. A subset from one of the classes is called two-linked if it's a connected subgraph of G2, the square of the graph G. So the square of the graph G is that you put an edge if two vertices at distance at most 2. So maybe a simple example is then this part is tooling, because in G squared we get a path. And the tooling component is a maximal tooling set. And actually what we proved, and maybe that's the main theorem, that if we look the independent sets in the middle two layers, then almost all of them admit the structure that I described, this easy structure. So what is this? That we can choose one of the parts, either the bottom or the top, and then looking the tooling the components, then all the tooling components have size either 1 or 2. So that the trivial description is actually best possible. And the proof use this graph container method. And as I mentioned, we run into trouble giving a formula for this, and we had to use this polymer method, which was nicely written down in the Jensen and Perkins paper. And just it's kind of a fun fact that to apply the polymer method, we have to check on some convergence, and to prove convergence, one has to use the graph container method that we use to prove this theorem. So things are somehow really connected to each other. So in the next 2 slides, I try to explain this method. So in this setup, so we have the this top and bottom layer. Then let's say that A is in the top layer, and the A will represent this defect set. So A will be subset of the independent set. And in the proof, it's much easier to work with the closure of A instead of A, where the closure of A is a set where we put some vertex to the closure if its neighborhood is already in the neighborhood of A. And this graph container lemma is the following. So if we fix some A and B, where A is the size of the closure of the set A, B is the size of the neighborhood of A, then the number of choices for this set A is upper bounded by this complicated formula. So I try to explain a little bit that what is behind the formula. So we have this condition that A should be at most half
József,
of the...
sorry, could you again say what is this G of AB?
So
number of
G
such
of
independent sets?
Okay. I plan to do it somewhat later, but maybe it's useful if I do it here using that I can draw. So I have, let's say, the K layer, the K minus 1 layer, and I want to count independent sets I. So I have this defect set A in 1 layer, and I want to count the number of choices for A, because I want to put A into my independent set. But when I look this neighborhood of A, then if A is subset of the independent set, then it implies that an A intersection I is empty set. And GAB is counting this choice of A's where we have some connectedness condition on A where we know the size of B. Size of the neighborhood of A, which is B, and we want to count these sets. Does it help a little bit?
Yeah, okay, so these are just the choices, okay. Just,
and
yeah,
I try
the
to...
choices of A. Okay, good.
Yes, I try to explain a little bit this and try to motivate it. I'm not going to prove this. I just want to give a little thing. But maybe this is useful setup to see that why is that I try to count A. I try to count A that because that's the part that I want to put to the independence set. And the size of B is important because it's kind of the saving, because if B is bigger, then we save more, that we know more vertices which are not in the independent sets. If I try to show what is on this slide, and if you have more questions, then we can discuss.
Great, thanks.
Okay, so somehow it's a useful assumption that A is at most half of the layer, because it's really useful that B is bigger than A. And we have isoperimetry property that it is the case when A is at most half of the layer. So if you look the formula, then the n choose K is just kind of trying to locate where to put the set A, because the layer is big. If A is small, then we have to start from somewhere. It's kind of a route for A. And I removed the writing. So this 2 to the B and this exponential term is practically the main technical work to identify for the closure of A, and then given the closure of A, we want to find actually A, and that's where the fight is going. And yes, so why is important this form? This bottom line is that I explained before, that if A is part of the independent set, then the neighborhood is not in. So when we do the counting for the independent sets, then we gain this factor of 2 to the minus B, which offsets this 2 to the B from that counting. And the main saving, where we save in the counting this exponential factor. And if B is reasonably big, I think I have something on the next line. So if A is small, then things are reasonably easy, because one vertex, then it has k neighbors. And then if we have just few vertices, then if A is small, then NA is big, so we get the difference is big. So e to the minus k squared is killing this n choose k, and it kills the number of choices for A and B. And in general, it means that the number of independent sets where this set A is big will be small compared to the total number of independent sets. And I think that's all that I tried to say about the graph container method. I think my slide is the application. Is any question on this?
Well, I would be very happy to hear more details about that, but I guess we can postpone it until after the talk, or I don't know, maybe I should just look up the paper.
Is any quick question about this? So this I put already 3 times before. This lemma is from Sapozhenko's original paper modulo some technicalities. So it's not, this lemma is not ours, and this lemma appears in David Galvin's paper he wrote, expository papers, where he nicely explains how to prove it. It's not trivial to prove it. Even that I explained how to do the standard graph container. Here, it's quite sophisticated, because if you look, we don't only count independent sets. We are counting sets A, which, so it's a slightly different. Okay, but let me try to give a sketch of the proof of this result. So I want to prove that in almost all independent sets, we have only tooling components of size 1 or 2. And the proof idea is very simple. Just you have to think that you have 2 sets that you want to prove that one set is bigger than the other, but we are not able to write up the formulas. Then what one could try to do to prove that one set is bigger than the other is that just compare them. That's saying that one of the sets is, let's say, 10 times bigger than the other, and I didn't put up this very simple graph theoretical lemma. But if I have a bipartite graph of sizes x and classes x and y, and if I know that the degrees in x are much bigger than the degrees in y, then from this we can conclude that y is much bigger than x. Does this make sense? So again, we have a bipartite graph. In one part, the degrees are d. In the other part, the degrees are delta in average. If d is much bigger than delta, then the class y is much bigger than x. And I try to use this. So I will set up bipartite graphs in the following way. So for this, I need to write up some functions of an independent set. So if I is an independent set, then I define Ci to be the set of two-linked components of sizes at least 3, and I assign a weight function which counts the neighborhoods of these components, and I partition the independent sets according to the size of their weight. So I put into UI the independent sets where this weight function is I. So I have U0 where I don't have a tooling components of size at least 3, and I have this UIs where it's important that I is at least 3D minus 3 because the tooling components has size is at least 3, and if you have 3 vertices in a layer, then the neighborhood is at least 3D minus 3 in the hypercube. And in order to, and we want to prove that U0 is much bigger set than any of the sets UI. If I prove this, then I prove the theorem. So I want to prove this for every I separately, and I use this simple trick about bipartite graphs. So I make bipartite graphs with the one class is the set of independent sets from U0, and in the other class from UI, and I put an edge between 2 independent sets. If I can get from one independent set the other the following way. So I have
József, sorry, one more question. What is D? D is the dimension of the space, or?
What is D?
Of the
Sorry, D is K.
D is K. Okay.
Sorry, I changed notation, but it was hiding somewhere. So just to back here, what I claim that if you have at least 3 vertices in one layer, then their common neighbor within the cube is at least 3k minus 3. Because it's a k regular graph, and you can't have many common neighbors.
Okay, good.
Okay, so I have I, and I put an edge between I and J if let's say I have this three-link component of size at least, or two-link components of size at least 3, and my operation is that I remove B, and instead of NB, I put an arbitrary subset K. Okay, again, so what's happening that between I and J, I have this operation that I can remove the large tooling components and add some arbitrary subset from their neighborhood. And what is the upside? So what are the degrees for this bipartite graph? So if I take an independent set from UI, then I know that its degree in the bipartite graph is 2 to the I, because this had size I by the definition, and K was an arbitrary subset of this which could be added. And then to count the other degrees, we just simply use the Sapozhenko's graph container lemma to say that to get an you have to count the number of ways to set up B, and maybe I don't put up many details. I just say that by this graph container lemma, we can say that you cannot do it many ways if you plug in the formula. It's kind of computational, so I did not intend to show. And then this gives that the degrees in this part of the graphs are really small. So the conditions are satisfied that for this auxiliary bipartite graph, the degrees in one class are much bigger than in the other class, and we conclude we have the conclusion about the sizes of the classes. So that's what I try to tell about the proof. Is any question? So in the rest of the talk, I just try to tell stories and related results, so I won't be technical anymore. So first I would mention briefly that how to get a formula, but I avoid all the technicalities. So if to get a precise counting, we build up polymers. Okay, I'm not saying what polymers are, so maybe I just skip this part because
I can just make a small remark that we actually heard Will Perkins on this seminar talk about this article some months ago. So I guess some of the audience
yes,
remember.
I think maybe Will Perkins or Jensen was talking about it.
Yeah, Will was talking about it here on this seminar. So.
Yeah, so it's very abstract thing just to define. It would take half an hour the model, but somehow the objects are these tooling components, and it's very useful to count the small polymers, so like the small tooling components. And there is a theorem of Kotetzky and Price, which says that if some certain convergence conditions are satisfied, then the small approximations are really precise. And this graph container lemma is used to prove the convergence of the cluster expansions. And somehow, if somebody understands the setup, which takes a couple of days, then it's a very useful. So I just wanted to advertise that method. We actually just followed closely the Jensen-Perkins paper and modified their proof to our setup for the precise counting. Okay, but now I promise to be non-technical. So I would like to talk about a little bit about the number of maximal independent sets in the middle layer. And that was actually more studied than the number of independent sets. This question was raised by Dufus, Frankel, and Rado, and they gave some lower and upper bounds, and they conjectured that the lower bound is best possible. I will explain a little bit later what is behind this formula. And Ilinko and Khan proved that the lower bound asymptotically is best possible, and they actually put up a conjecture that what should be exactly the lower bound. And I explained how this conjecture was coming. So we fix a direction in the hypercube, like fix a coordinate, which can be chosen n ways. So this explains this factor and there. Then given this direction, I can find an induced matching of size n minus way, choose k minus 1. So how to get this? I look n minus 1, this has size n minus 1, and I choose the rest of the k minus 1 elements, and this is an induced matching. On induced matching, I meant that I don't have edge between matching edges here. And now how to count maximally independent sets. For each edge, I choose either the top endpoint or the bottom endpoints. So it gives this 2 to the n minus 1 choose k minus 1 factor. And I have the free choices because it was an independent, because this was an induced matching. And for the rest of them, I just fill anyway I want or forced. And I generate this many different maximum independent sets. So this is the lower bound. And Ilinka and Kant conjecture that this way we can generate most of the maximal independent sets. Any question on this construction? So here I try to do the same defecting as we had for the hypercube. So in this picture, this edges on the left side correspond to the induced matching, and on the right side I choose 2 sets in the form like that a plus 1 and a plus r plus s, where rs are just directions, and I add these 2 vertices to my independent set that I want to generate. And if I put them to my independent sets, then I have to remove their neighborhood. And for the rest of the induced matching edges, I still have 2 choices to make. So how many maximal independent sets I generate? So for R and S, I have about K. Actually, it's yes, K choose 2 choices. Given the choice of A, which is about n minus 1, choose K, and I lose 2K induced matching edges. So I lose about 2K choices for having 2 choices. So I generated about this many maximal independent sets times 2 to the rest of it. So this is the surplus as a multiplicative factor. So it means that I improve by this with k to the 3/2 the trivial lower bound. Any question on this? It was maybe a little bit rushed. Okay. So this shows that the conjectured lower bound is not correct, and one can try to boost up this construction by taking more pairs of this like this dotted edge, because it's not an actual edge, and we were hoping to get really many new maximal independent sets, and it was a little bit disappointing that all that we get is like instead of having the polynomial factor in front of the exponent n to the 3/2, this came up to the exponent as some constant times n to the 3/2, and we were a little bit puzzled. We had this construction with Andrew Treglown and Adam Wagner, and actually for a while we were thinking that we made some error, but we couldn't improve it. And there was a strange thing that when we compared this formula with our new result, then if we compare then this bound, this 2 to the n minus 1 choose k minus 1, it's comparable to this 2 to the n choose k. And this error term n to the 3/2 looks to be the same as here the second error term. And we get really puzzled at what's happening with this error term here, with this 2 to the k. And after some thinking, we realized that the reason for this is that when we counted independent sets, then the first error term counted the singleton tooling components. The second error term counted the tooling components of size 2. And if we look back this, maybe I'm not able to look back. If we look back this picture, then if we make some model, then this is on the defect size, and this has size always at least 2 for some reason. So there is no singleton tooling component. So that's the reason that this factor disappears, and that's what we hopefully proved very recently, that almost all maximal independent sets in the middle 2 layers has actually the structure as we showed in the picture. And the last slide is about going back a little bit to Erdos Rado. That so the Erdos Rado theorem said that the maximum size of an intersecting K uniform hypergraph has this star structure. And a couple of years ago, we looked that what is the structure of a typical intersecting family, and we proved that if n is somewhat bigger than k, like 4k instead of 2k, then a typical intersecting family has this star structure. And this was further improved by Frankel and Kupaski and us, where we pushed down n to 2k plus some error term to have the same statement that almost all intersecting families have the star structure. And now we think, but we haven't done the work yet, but I think we have all the ingredients that, given this transformation of the Erdos-Rado problem to counting independent sets, we can get some conclusions about almost all intersecting families, and maybe we can put here +2 instead of the root k. But this work needs to be still checked. But at least it gave me a good opportunity to cite the organizer. So that's all. Thank you.
Thank you very much.
Thank you, József.
Are there any questions? Okay, I have one. So you told that you have this improved lower bound for the maximum independent sets, for the number of maximum independent sets in 2 layers of hypercube. But then you wrote that you proved that almost all maximum independent sets are like on your example. Does it mean that the upper bound is the same or not? So
I try to go back to my example.
Mm-hmm.
So maybe I run through on this, that here I chose one defect pair, and obviously I can choose many of them if they are far from each other, and then that what actually boosted up the formula. That's, I think I forget to mention that the way how we get here this extra term was that that we chose many of these pairs, and the result that we claim to have, that we can generate almost all of the maximal independent sets the way that we choose these pairs where their neighborhood are not intersecting.
Mm-hmm. Okay.
So so somehow, even if we look back to the very beginning, that when we counted, let's say, independent sets in the hypercube, and we look these defects, then for the precise counting, it was important that the defects are distance more than 2 from each other, that their impact on the neighborhood shouldn't perturb the final result. And the statement is that when you choose these defects here, then these defects should have behave the same way, that they should be far from each other. And if we do computation, then we haven't worked out all the details, and it gives some estimation that actually how many of these defects will show up actually in most of the cases.
But is there any conjecture on what is the right answer, or you think that your lower bound is correct?
No, so that's what I am claiming, that this formula is practically precise. Just I mean, when we say that we have the characterization that almost all, then from this we can get a formula. We have some computation which counts it directly. In case if there is some error, then we just run the polymer method, and then from the polymer method we can get those numbers. So this kind of big computational tool that we use as a black box as of now.